Hope you're all good. Sorry for the couple of minutes we wasted it now. It can be. I like them big. I like them plump. As Moto said in Madagascar too. I like the screen to be big as well. So I see Hebrew, so I love. Okay. We still talk about inner product spaces, but all the Gram-Schmidt and Gram matrix and whatever we finished the last lecture with, we're done with that. We can start a new subtopic inside the big subject of linear of inner product spaces. Now, just like the Gram matrix we finished with last week, I want to talk about something not very big, a couple of minutes. Let's see how if I want to prove it or not. In Hebrew, it's called משפט ההצגה של ריץ. ההצגה, how do I say it in English? I use, as usual, the Wikipedia representation. Okay, that's good. Let's copy that. We still talk about inner product spaces. Okay, so Riesz representation theorem. Riesz, may he be blessed, says the following. Let V be an inner product space over a field F, and let T from V to F, the range is the field itself, be a linear transformation. Then there exists a unique, let's call it, I don't know, A in V, such that the image of V is the inner product of V with A for every V in V. For example, we look at, let's say, V is Rn with the standard inner product, and let T from V to R. It's only true about linear transformations from the space to the field. That's why the image is stellar. And let T מ-V ל-R be the following linear transformation. For example, T of vector x1 to xn is the sum of all the x's. Now the vector, what? With the 1, 1, 1, 1, 1, 1. Vector of all ones, yeah, correct. Indeed, the vector one, 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 T of x1 to xn is the, he says that your internet connection is unstable. It's not my internet connection, it's the university's one. Not offended, but maybe I am. x1 to xn and the vector 1, 1, 1. They are the same as the sum of all the coordinates of the vector for every x1 to xn in Rn. Now, what Riesz says is not just there exist such a vectors, it exists for every linear transformation from V to F, and moreover, it is unique. There only one vector we can talk about. So basically what Riesz says is that we can think of linear transformations from V to F as a inner product with some constant vector A. One can think of another example, such that more natural one, maybe, such that the trace of a matrix takes a matrix to a scalar, and the trace is a linear transformation. So in the standard product of matrices, the trace of A, B, transpose, etc., we can find the specific matrix that every multiplication A with that matrix give us the trace of A. It's probably the identity matrix, but there's another example, and I want to talk. Don't know how much I want to elaborate, but explain why the theorem is correct. Yeah.
Like there's an input of a vector, and that's the product with a specific vector that is dependent, like the vector depends on the matrix of the information, but it's one single vector, right?
Yes, as long as the transformation goes from V to the field F, not a different space or inner product space W. Sammy, any questions?
No.
Good. Okay. Let's prove. You know what? Let's prove the theorem. We need to prove two things. First of all, that such a vector does exist, and secondly, that it is unique. Now let's start with existence. Existence. We need to show why there is a vector A such that let's see how we use it. B from V1 to Vn orthonormal basis of V. Last week we showed that whatever V is, we can achieve an orthonormal basis, finding a basis and then applying Gram-Schmidt. Is it safe to lay down the bottle without closing it? I'm not sure.
Or are you're willing to make it?
Yeah.
Is it are still willing to take the measure?
My only problem with the water spilling is that I will be thirsty. It's not the floor getting wet. Yes. We have a guest. Unlike the people guest, they are not frightened, not running away. B an orthonormal basis of V, and let B. It's a field. It's like intuitively of scalars of numbers. So let's call it just C with 1. B basis of F, and it is normal, which is very boring. But right now we can think of the image of V is 1 multiplied by, or TV multiplied by 1. So by the definition of coordinates vector, we get the coordinate vector of TV by the basis C. I mean, the basis C only has 1 as an element, so something multiplied by 1, the something is the coordinate. So it is the coordinate vector of T of V. And now I'm using something you probably saw with Erez on linear algebra 1, which was extremely fun. The image of TV by the base CC, coordinates by the base CC, is the multiplication of the matrix of T from B to C and the vector V by the coordinates of B. Okay?
T equals 1, yeah, what do you mean the standard base?
Yes, I mean F is a very boring as an inner space, in product space, or as a vector space generally. It's just a space of scalars. But every scalar is A multiplied by 1. So 1 is the basis of F. Every non-zero scalar is the basis of F. When you think of F as a vector space. Okay, so this is a theorem from probably this theorem from linear algebra 1. It's practically the definition of T from B to C, but as long as it's true, why do we care? Now I'm using some tricks here. Just want you to understand tricks I'm using, not how I think about them. I thought about them from in the first place. Remember the 5th of November and the fact that this is a scalar. So we can, in Hebrew we say litalel. It's not a good word, but we can at least transform it. Let's write it down explicitly. We can put the transpose there because it is a scalar. We march forward.
What V?
T of V. Because T is from V to F, which is a set of scalars. Using the transpose on the multiplications of things is using the transpose on each and every one of them, but changing the order, switching the order of the friends in the multiplication. This is the transpose of T. Now, what can we say about here the transpose of T? Yes. You know what? Let's write it down here. I mean, you can insert the T maybe inside the square brackets, but I don't need it right now. On the other hand, what can we say about V multiplied by A? On the other hand, we can no, express is the right word. Express V multiplied by A as a multiplication of vectors and the matrix, Gram matrix. We introduced, we showed, we discussed in lecture number 10, which was extremely fun. And as I said in lecture number 10, the only thing right now, at least, that we need to know about the Gram matrix is that the inner product is the multiplication of V transposed using the coordinates of V multiplied by the Gram matrix of V multiplied by the coordinates of A, which is the second vector here in the multiplication. But another thing we mentioned about the Gram matrix before, you know what? Let's remind it. Delete the V here. We know that the ij element of the Gram matrix, that's the definition of the Gram matrix, is the inner product of the Vi and the Vj from the basis B. And as we mentioned in lecture number 10, because B is an orthonormal basis,
Not data, sorry, but
Identity. You are absolutely true. You are goddamn right, as Walter White once said. It's just the identity matrix. So, what do we have here? It is just the identity matrix, which we don't need to write down when we multiply things. So it is the multiplication of the V transpose, coordinates by B, and the coordinates of A by B. So what do we have here? We get, what did we get? By now, on one hand, PV is the multiplication of VB with some weird transposed matrix. And on the other hand, we got that V with A is the multiplication of V. No, I missed the transpose here, my bad. No, it should be the same, but it's transposed, I missed it. V with A, the inner product is V transpose by V multiplied by A by B. So what do we need to find? We need to find such an A that this matrix and this vector are the same. If there exists an A as such, we at least know that such an A exists. Now we'll talk about the uniqueness.
inner products, no, yeah, that. Why can't we just say that it's equal to the multiplication with the gram matrix? We know the gram matrix is just the inner product of each of the.
Yes, we said it last week. We said it, and as far as I remember, we didn't got much into it. Why is it true? But it's just a nasty multiplication of matrices. You write down explicitly with sums over sums, as we like to write explicitly multiplication between matrices, and you get the result of the inner product. It's not a fancy mumbo jumbo. It's just sums over sums.
Well, the multiplication, the inner product between B and A is a single element in the whole matrix, right?
No. The elements of the matrix are the inner products between the elements of the bases. While V and A are not elements of the basis, are not necessarily elements of the basis, they are a linear combination of such elements.
So the gram. Okay.
So the gram is actually the scalars in the linear combination. And we already know that when it comes to orthonormal basis, the scalars in the linear combination are the multiplication, the linear products of the vectors. V with V1, V with 2, etc., etc. So on the other hand, so we are left with one thing. Why is there an A or AA or whatever you say it, such that A coordinates by B is the transpose of the matrix of T from B to C. Now that's a simple question. You know what? If I think I forgot something, because we're not talking about R, we're talking about general field, which can be the complex number as well.
Yeah, I was going to ask that.
It should be the conjugate. It should be the conjugate.
Transpose equal to right R is the conjugate, is like the transpose and the conjugate of the element.
Generally speaking, the answer is yes, but right here, I use transpose, which is totally fine because it's scalar. I don't need to use here the start in order to prove my statement, but it is the transpose of A.
Yeah, can I ask a question?
Yeah.
I'm getting mixed up on the the notation, the
Yeah.
A with the square brackets, and then the B, what does that mean?
The coordinate vector. I mean, A is a linear combinations of the a linear combination of the vectors of B, because B is the basis. A is some A1 multiplied by V1 plus A2 multiplied by V2, etc., etc. And the vector of the scalars of A1, A2 is the coordinate vector. It is denoted by the square brackets and B.
Right, okay.
So the only question is, why do we have such vector? It is equivalent to, I mean, applying the complex conjugate on the two sides of the equation, we get that the coordinates of A without the conjugate is the conjugate of this matrix, which can be denoted with a star, as we have mentioned someone before, and we will discuss it very later on in what's left from our course. It's equal to 2, and this is correct. And we know that such a, not such NA, weird, such a exists because the coordinate vector is onto, is surjective. Every vector is the coordinate vector of someone. So yes, there is a someone A that satisfies this equation, as we've already explained. It means that yes, there is an A such that the image of V is V with A. Now it's the same A for every V. Because as you mentioned before, A only depends on the transformation T, not about the specific vector V we put in T.
Yeah, but I don't get it. Why is there an A such that the conjugate of A equal to transformation, but it's you mean because you have to multiply this the vector you want with A to get the dot product, like the transpose of one times the second one and get the dot product. That's why you can say just the matrix is just that the vector.
Yes, I mean, I know this one to be true, and I know that one. Now they both have VB transpose multiplied by something. So I need to show that this something are the same, or more precisely, there is an A such that they are the same.
Okay.
Any other questions? Sammy?
Nope.
So the second step is the uniqueness. Why is it just only one? Uniqueness, that's how you write it down. Hello, it's with Q, of course. More than that. I know that I want to watch a fun word in English. I'll show you. Talked about probability. You study probability this semester?
Yeah.
Yes. So you know that I already know this word, so I don't have to show you anything. Talking about the discrete distribution, the geometric distribution is the only one that satisfies the memorylessness property. Yeah, and when it comes to the continuous distribution, the exponential distribution is the only one that satisfies this property. So now I just found it last week. I teaching Brute probability this semester. with the Hermitian. It's actually
You mean you could have another review with this semester?
no, I'm teaching it not here. I'm teaching it on the Hermitian. No, actually here in Bar Ilan, and never taught probability for computer science. No, I want to say that first of all, in Hermitian, basically our courses are much more difficult from theirs. it's מכללה, it's university, etc. But specifically, this the probability course is it's well respected. It's not maybe not as difficult as here, but it is quite difficult. And second, I just thought about it last week that the word is memorylessness. So all the suffixes there in the end. Uniqueness. Okay. Say the easier part probably. Assume that there is a V such that T with V is the multiplication of V and B. Semicolon. We know that T with V is the multiplication, T of V is the multiplication of V and A. And we need to show that A and B are practically the same. Now it's something similar to something we've already shown when we first discussed inner product. We know that if they are both equal the TV, they are equal. And it's true for every V. Now we show that it is enough to conclude that A and B are the same, but let's walk through the little proof of it. One more time, as Daft Punk used to say. We have VA minus VB is 0.
The problem here is that none of it's like it's not for one B for every vector.
For every vector, yes. For every vector V is just as multiplying with the same vector A. Just like in our example. Whatever vector you take, multiplying it by the vector 1, 1, 1, the same 1, 1, 1, yields the inner product.
Yeah, what I mean is kind of have the same result from two different vectors, right? Depending on what the
Yes, the inner product is not injective or something like that.
yeah.
Yeah, it's not. And we have here the multiplication of V with A minus B, which is 0 for every V.
Here too, because you have an arbitrary rate or an arbitrary field, like for the complex field, it will be different.
No, we know that even if it's the complex field, in the second coordinate we have the almost linearity. The only difference is when it comes to scalars, you should conjugate them. But here the scalar is -1, which is a real number, so we don't need to use the complex conjugate. It is 0 with every or for every. For every V. So we know that means that A minus B must be 0, which means that A and B are the same. We already mentioned some lectures before. If the multiplication with the same vector is always 0, then the vector must be 0 itself. Okay, so that's my proof. A long, nice, meaty one of Riesz representation theorem. Any questions about that?
I mean, my question, which you will probably answer in the next section, is how does this help us with anything taking into account that multiplying two vectors, or we're multiplying the multiples of one vector with the other vector? Like the transformation is just a dot product. How does this help us in any way? Because
First of all, we know some things about that product that maybe not exactly know about linear transformations. So saying it in the language of the dot products can help. Secondly, I may use or may not use it in my proofs to come. about the what's left from our semester. And thirdly, on the other way around, maybe we can use our knowledge about linear transformations to say some things about inner products we didn't know how to say before, Riesz representation theorem.
Yeah, you don't have to prove linearity for this, or for transformations and not follow those.
No, I know it is given to me that T is a linear transformation.
I've got a question.
Yes.
Shouldn't it be the conjugate when we go from v dot a minus v dot b to v dot a minus b?
No, can you repeat the question?
The second last line, when we go v dot a minus v dot b, like a bit after that, shouldn't it be the conjugate?
Talking about this arrow?
Yeah, why isn't it the conjugate?
I'm using the almost linearity in the second coordinate.
I thought linearity is only in the first coordinate.
Yes, and in the second coordinate, we have what we called the almost or half linearity. I mean, if we walk through the all the process itself, I mean, we are changing the order of the vectors. It is A with V and B with V. And when it comes to complex conjugate of sum or a difference, doesn't matter. We can put the conjugate all over the difference. Copy put out. There, under the safe roof of the conjugate, A and B are in the first coordinate. So I can look at the conjugate of A minus B with V. And then you conjugate again, switch sides again to get V with A minus B. Now it will work, as we mentioned before, for every vectors. The only difference between the first and the second coordinate is that the scalars in the second coordinate should be conjugated. It's not exactly linearity, we call it almost linearity, but here the scalar is -1, so we don't see the complex conjugate because it's a real number.
But if the scalar was a imaginary number, then we
Yeah, if the scalar was something like, I don't know, I or something like that, then it should be minus I again, the complex conjugate of I, when I put it inside the second coordinate.
okay.
Okay. And okay, let's move on to our next main and probably last big subject for the semester, but it's still under the big headline and the roof of inner product spaces. I call it the conjugate transformation, העתקה צמודה בעברית. Let's see if that is the right. No, it's called Hermitian adjoint. Okay, I thought it would be conjugate. It may also be Hermitian conjugate. Whatever. Let's write it down. Hermitian adjoint. Also called Hermitian without the Hermitian conjugate or just Hermitian? It's the dude's name, right? He's deceased a long time ago. Hermit. Charles Hermit, as far as I remember. Yeah. Okay. What is all about? Let T be some linear transformation between two inner space products. Spaces, let U and V be N inner. Is that right now? No, it's with N. It's that inner product spaces over a field F, and let T from U to V be a linear transformation. The Hermitian adjoint, or just the Hermitian, okay, adjoint of T is denoted T star, semicolon. It is a linear transformation T star from V to U, all back to U, that satisfies the following equation. The inner product of TU and V is the same as the inner product of U and T star V for every U and U and V and V. Right there. Comma. Semicolon. Huh? Moreover, just a sec. Moreover, it is the only linear transformation that satisfies this condition. So I claim here three big things. First of all, that such an T star exists. Second, not trivial. Secondly, it is the only one that there's only one that satisfies that. And thirdly, it is a linear transformation itself. Now, there is a different question. Let's agree that it's all true. Given the specific linear transformation T, how can we find the T star? That's a different question, more technical. Yeah.
So the EUV is the dot product of two vectors from B and U V star B is a dot product of two vectors from U. And that's what we're saying is equal. Like the first part is two from the second one is two from U and they can be from.
You are correct. Yes. Yes. This one is multiplying the inner product of two vectors of V, and this one two vectors of U. They are because it's an inner product. They are both scalars and in the same field F.
Yeah, but then it's we are giving the transformation a value of this dot product and not to the space. Because like if you were telling me we have this certain dot product and we take the transformation from the whole dot product and then that's the result of some other dot product from another space, then we are saying, okay, we transform this dot product to this dot product in another space. But here we are saying, okay, the values of the two dot products have to be the same, but here we're changing the values. Like in the first case, it's the first vector. Like the dot product space is defined by the second vector on the dot product, right? So
What do you mean? Defined by the prove them. The product is of two vectors.
yeah, like the whole dot product of U is defined on the second vector or not necessarily.
No, the product is always of two vectors. Now, I say, assume all of it is true. How can we find, and it's another non-trivial claim, how can we find the T star? Second T star. We take B and C. Or normal bases. Bases, that's the plural,
No.
whatever. Is the plural?
Bases?
Bases? No. Base side, whatever. Bases. Orthonormal bases of U and V. And then the matrix of T star from C to B no. Okay. From C to B is the star of the matrix of T from B to C. And when it comes to matrices, we know what the star means. It's transpose and the complex conjugate, that's right. So if you want to specifically find T star, you need to use, you can find some of the matrices that represent it using specifically orthonormal bases. And when we have a matrix using orthonormal bases, we can use we can find the T star itself. And it's now, let's get an example, and then we'll start to discuss the proof of all the non-trivial stuff I just claimed here. For example, I don't know, let's be some T from R3 to R2 with standard inner product, as I mentioned before. If I do not mention what inner product we talk about, it is probably the standard one. T from R3 to R2 be the following linear transformation. T of x, y, and z is, let's say, x plus y, x minus z. Okay, from R3 to R2. In order to find the T star, we need to use some orthonormal bases. Now, we can take B to be 1, 0, 1, etc., etc. And C with 0, 1 and 1, 0 as orthonormal bases of R3 and R2. Standard product here enough. Totally fine. And we know that the matrix representing P star is the transpose of the conjugate of the matrix representing T from B to C. But when we talk about the standard bases, we know pretty easily how to write down the matrix. It needs to take a vector of 3 coordinates and put it as a vector of 2 coordinates. So it should be the following matrix. 1, 1, 0, and 1, 0, minus 1. We should transpose it and then conjugate it. It's all in R, so it doesn't matter the conjugate, the complex conjugate here.
It doesn't matter that main bijective or surjective.
No, no. Mean nothing of that. We may discuss how these properties affect the properties of T star, but by definition, we don't need to know anything about T. It should be a linear transformation and nothing more. Okay, transformation of the transpose of this matrix is with 3 rows and 2 columns. It is 1, 1, 1, 0, 0, minus 1. And you're writing in explicitly, T star takes the vector xy from R2 and gives us x plus y, that's the first row, x and minus y. These are the second and the first row, that's what they give us. I mean, yet again, how do I know what the matrices representing the linear transformation by the standard bases are? It's the same as multiplying the matrix with the vector. So which matrix I multiply with the vector x, y, z and get the vector x plus y, x minus z is that matrix. And which matrix, this is the matrix representing the T star by the standard basis, it means that T star itself is multiplying this matrix by the vector, general vector R2, which is xy, and we achieve x plus y, x, and minus y. Now, I claim that if you take some vector x, y, z, yeah.
Okay.
Yeah, it's common. It's three coordinates. You know what? Let's change the letters. It's different things. A plus B, A minus B. So now what do we claim? We claim that if you take T of some general vector x, y, z of R3 and you multiply it by some general vector AB, it will be the same as multiplying the vector x, y, z with the image by T star of the vector AB for every A, B, and for every x, y, z. That's what we claim here. So indeed, let's see that it is correct. The multiplication of T, X, Y, Z, and AB is the multiplication of X plus Y, X minus Z with A and B. Do I complete it right? There's a little soft sound of rain. It's actually my battery trying to not kill itself. It is x plus y multiplied by a plus x minus z multiplied by b, which is xa plus ya plus xb minus zb. And on the other hand, the multiplication of x, y, z and c star is the multiplication of x, y, z and a plus b, a minus b, which gives us first coordinate and first coordinate plus second coordinate and second coordinate plus third coordinate and third coordinate, which is, oh, how surprisingly true, is the same. Now, I claim, it's a big one, that everything I said it is true in the general case. There is such a T star, it is unique, it is linear transformation, and we can find it using orthonormal bases and this equality. And I want to prove it. I want to prove not of all this. I mean, we should probably take the break in the middle of the proof. But after we prove all of that, we can talk about the properties of the star you mentioned, bijective, non-bijective, and what can we say about that?
The homework is something similar.
It might be. I mean, we are getting closer to the end of the semester. Sometimes we're near the practice. Want you to submit some homework to be checked and graded about these important subjects. So maybe it's before me. I don't think he is, but I don't know. Any questions about the definition in my example? Okay. So proof. Let's see proof. Proof of the example. Proof what I stated. Yeah. First of all, I want to say that such T star exists. It is unique, and it is a linear transformation. Okay. What?
What do you prove about that specifically? I mean, you have a matrix and you do the transpose and the confidence it's still a matrix and it's still.
No, I want to say that we want to show that such T star that satisfies the main equation, this exists. That it is a linear transformation. That it is unique. And we can find it using this. All of that. All of the above. Okay. So, as you said, we're to begin with the start. How can we, first of all, write down that there is such T star, even without being a linear to summation or whatever. Okay. So, we know that let B, let P and U and V be as mentioned before. U and V are inner product spaces over the same field. So we can talk about equality between the different inner products. And T is a linear transformation from U to V. Yeah. Yeah.
Must the one be the same inner product?
No, they can be here in my example, it's the standard product, but it's a different one. Here it's for R3 and it's for R2. Can be a totally different inner product, but it should be over the same field. So the same field, we cannot make sure that these two scalars are equal with different sets. Okay, let's some U be in U. We can define linear transformation. Let's call it, I don't know, KU from U to F. No, from U, from V. It's the second one. From V to F by KU of some vector V is the inner product of V and U. No, of TV. I claim that this is the linear transformation. It's basically because T is linear transformation and it's an inner product, so they both satisfies the property of linearity. So KU will do the same. It is indeed, write down explicitly, it is indeed linear transformation. If we insert some, I don't know, A V1 plus V2, which is P of A1 plus V2 multiplied by U, we get, first of all, inside the first coordinate, P is the linear transformation. So we are left with A TV1 plus TV2. And using the linearity property of inner product, we can write it down as A TV1 with the U. So, tired today. Mouse. And it's TV2 with you. What? First of all, I save it. Secondly, I have the actual mouse here. So nothing works, I can get to him. Here is it. No, but there's no need of that. Or right now, at least. Okay. So it is linear transformation. It is transformation from V to F. So how convenient, we can use Riesz. Friend by Riesz. There is some unique vector. A, which is for U. For every V, TV multiplied by AU. Vector in V such that a vector in U, no, it's in V, sorry. That the KU of V is the multiplication of V and A of U. This is by Riesz. The linear of some vector is the vector multiplied by some specific vector. So we have that TV and U is V with AU. If we define or denote AU to be the T star of U, we get the desired equation. So now the question is that. Write down that. Now the question is, why this, I don't know, function that take the specific, take the vector U to the AU that belongs to him by Riesz theorem. is a linear transformation, and why is that it is unique? Why can we use some different linear transformation that satisfy the same? I mean, by Riesz theorem, there is a vector u that AU that satisfies that for every vector u. On the other hand, that's how I define the KU transformation, so it should be the same. Okay, so let's denote this AU by T star. But I claim about T star that it is the linear transformation. It will take alpha AU plus BU, and etc. Can split it as needed, and it is unique. We only have this one um, linear transformation that satisfies all this. Okay. Any questions about that? We've already mentioned. So let's begin with the linear transformation. We'll begin with the linear transformation, semicolon. Let U1 and U2 in U and some A, let's write down alpha, uses in F. We need to show that T star of alpha U1 plus U2 is alpha of T star U1 and T star U2. Now, T star is defined right now by this equation. We can conclude eventually that it can be computed by this method, but right now, it is the only way we can discuss T star using this equation. So, on one hand, what can we say about the, no, I say it's not one hand, will be only one move. Indeed, why not? Using some fancy word from time to time. Huh? Henceforth, yeah. Nevertheless, memorylessness.
You said that AU is a vector V, and we can represent it as T star from...
Yes, it's just a notation, but I claim that it is a linear transformation. If you take some different two vector U1, U2, and they both have the same A of their own, then the vector from Riesz representation corresponding with the linear combination alpha U1 plus U2 is the alpha of the vector of Riesz vector of U1 plus the vector Riesz vector of U2. So indeed, by definition, we know that TV for every V with alpha U1 and U2 is the same as no, contrary, what is that? V with the T star of alpha U1, U2. I want to talk about T star, right? V with the T star is, by definition, T of V with the vector itself. Yeah. Now, without the V here, this is the main equation. Okay? V I mean, T star on the right hand is just putting T itself on the left hand. Now, what can we say about this inner product? We have a linear combination here, but it's the second coordinate. So as mentioned before, we do have the almost linearity. I mean, the product of TV and U1 should be multiplied by the conjugate of alpha, not just alpha itself. So it is TV with U1 and TV with U2. I don't know if you can see it, maybe a little pale line, but it is alpha, the conjugate of alpha. And right now, we can use the same basic equation. You have, you know what? You have T on the left hand. You can change it, switch it for T star on the right hand or end, whatever, of the inner product. Then goes for the second inner product. And yet again, we can use the almost linearity in the second coordinate as well in order to pack it up back together to V with our alpha T star U1 plus T star U2. We used the basic equation fundamental. This one. All right. Yes. Different word. Second, and the almost linearity of the second coordinate. للسيروجين. How do you say it in English? When you do that and that. A, B, alternately. Okay.
So what I'm not understanding right now is you said how to prove that the star exists, that it's a linear transformation, that it doesn't say it does, right? Because how to prove
No, does what it does is the existence. There is such as so Riesz gives us the existence.
Oh, Riesz gives us.
Yes, there is a vector AU, and I just denote it by T star. Now, why do I denote it by T star? Because when it comes to the technical part of actually finding for a given T, it's using the star of matrices. Yeah. But it's just a notation. Now, we'll finish it quickly. We are proving that it is a linear transformation, and we are left to prove that it is unique. And then to prove the technical way of finding it with a star. So right now, what do we get? What did we get? For every vector V, the inner product of V with the T star of alpha U1 plus U2 is the same of the inner product of V with alpha T star U1 plus T star U2. And as we mentioned before, we know that if it is the same inner product for every vector V, then it is the same vector. As required, UEG. But this is the proof of it being a linear transformation. That's pretty bit easier to read later on PDF. Any questions about my proof?
Right. One thing about this, how you're proving that like you're what the if the product of EV and U was the product of V and V star and U.
I use this little tricky KU. I defined this as a linear transformation. It is indeed a linear transformation. So by Riesz, there is, it's a transformation from V to F. So there is a vector in V such that the transformation, the image of V, is the inner product of V with this vector. So instead of TV with U, we are given a V with something. And I call this something V star. Any other questions? Yeah.
In this case would be scale of the version. Right.
B?
Right, because you're defining B the result of the dot product. K and K is dot product, so the KB is scale at the
Yes. KU of V is a scalar. Okay. Any questions from you, the Zoomlings? The Zoomians?
No.
Okay. So let's take a break. 15 minutes netto. So we start again at 1 and let's say 36 minutes, something like that. We prove the uniqueness and we will move on. I'm stopping the recording. Please remind me to resume recording. Okay. We're going to talk about uniqueness, but we probably the same as the uniqueness of the A and B in the proof of Riesz representation theorem. Now, for uniqueness, assume that there is a linear transformation. Let's call it, I don't know, S from V to U, such that the inner product of TV and U is the same of V and SU for every U and U and V. Now we know that it's true for each and every one of them. So we do have, it is true for V star. And so they are both equal TV and U, then they are equal. As we mentioned before, it's the third time today, if the product with V is the same for every V, then it must be the same vector. It holds for every V, so they are the same vector. This holds. That holds whatever. For every U, if two, generally speaking, functions, and not just linear transformations, if two functions has the same image for every input, it is the same function. S is actually T star. So indeed, T star is the only linear transformation that satisfies what we mentioned before. And about the explicit way of finding T star using orthonormal basis and representing matrix of T. We can, of course, prove it, but I'm thinking to myself, should we prove it? Or can we? Yeah, move on to the this one, this equation. So you want me to prove it?
I mean,
Okay, so it's totally fine. Okay, so let's prove the last thing we claim without the proof. Okay, now. Lastly, let B, let's write it down explicitly, sum V1 to Vn, Vn orthonormal basis of U, and let C with vectors, I don't know, U1 to UM, be an orthonormal basis of V. We need to prove that the representing matrix of T star is the star of the representing matrix of T, using the same basis. Now, by definition, the no, should I do it that way? I have two different kind of methods. We want to prove equality equation between two matrices. So we need to prove it for every element. For every I and j, the I and j element of the matrix on the left hand is the same as the one on the right.
yeah, I mean, we did prove that the conjugate of a matrix is like, I mean, did we define the conjugate of a matrix at any point?
Yes, we're conjugating every element. Yes. But on the other hand, a different method to prove it can be the following. We know that the representing matrix is the only matrix that satisfies. We can show that they are the same matrix for same element for every I and j. Semicolon. Alternatively, we know that T star from C to B is the only matrix satisfies multiplying T star from C to B with some vector of coordinates C, we get its image by the coordinates of B. So it is enough to prove that the matrix T from B to C star satisfies the same. So we can do it that way or that way. Okay. I think I'll go for the first way, proving that it is the same element for every element, but one can try that and probably succeed. We will show that this is correct for every I and j. We know that T star can move to the right side of the inner product. It should be written here, yeah. And that we can express, write down, whatever, inner product, and inner product using the Gram matrix we mentioned earlier and in lecture number 10. So let's begin. The multiplication of the product of TV and U is by the way of using Gram matrix is the transpose of the first vector using coordinates, and let's write down with thicker brackets. Transpose multiplied by the Gram matrix of the bases multiplied by the coordinate of the second vector, but conjugated. So let's write down again with the conjugate overhead. And right now, again, we know that two bases C and V are orthonormal. So GC is just I, as we've mentioned earlier in some other proof. And of course, we don't have to write down the multiplication by I. And again, GC I, because C is orthonormal. Now, as we mentioned before, the TV of C is the multiplication of the matrix TVC and the vector V with the coordinates of V. So we continue here. This is the transpose of TVC. So it is the transpose of this multiplication. And we know how to transpose multiplication of the vector. We are transposing each one of the vectors, and moreover, we are switching the order of the participants of the multiplication. So it is V transpose. It is T from B to C transpose. And it is U from above C conjugated. On the other hand, so we got that the multiplication of TVU is this nice little fellow. On the other hand, this multiplication is TV with U, which is V with T star U. And we could go through the Gram matrix all over again. It's the vector V using the coordinates of B. Suppose multiplied by the gram matrix GB. Sammy, you are from GB, right? What do you call this joke? And the vector of T star using V, but conjugated. Yet again, GB is I because it is an orthonormal basis, and we can throw the I away. We're left with T star B. Yet again, we know what T star B is. We know that T star B is the multiplication of the representative matrix of T star by from C to D multiplied by the vector represented by C. No, it's not V, it is U. No, so I changed the my bad, I changed the order of the vectors here. Right, because something I missed something about the order of the base. I mean, C is the basis of V. And here I use the vectors of V using C, but I changed the order of the vectors. I mean, here I use the vectors of V. I mean, I swapped the vectors. The vector V is from U here, and the vector U is from V. I mean, U is from V, so you represent it with the base C, and TV is a vector in V, so represented with C. I switched the order of the basis. I think the best way, it's all good, but the best way to write down as we are used to, I mean, the little v is in the space V, and the vector U is in the space U, is just change the words here. I mean, B is the basis of V, which is pretty logical because it's the vector V's, and C is the basis of U because the vector U's. So that's my only mistake, or it's not mistake. That's what we're not used to. The vectors V are in V and not in U. The vectors U are in U and not in V. So it's all good right now. Just it was weird, but not false. Right now, we are talking about the conjugate of a multiplication. We know it is the conjugate of each one of the participants of the multiplications. How do we say it in English? I mean, in Hebrew, say you participate in a machpelah, you are mukpalim. Members, but you have a... No. Do you have the fancy word like multiply, something like that? Don't multiplicitants. Okay. So, well. What do we have here? What do we have here? The multiplication of V transpose by V. With D at the end? You said it, multiplicand. Yeah, okay, it's a fancy word. And when it comes to summation, in Hebrew it's mechubarim, the participants of chibur. And how do you say it in English? Yeah, but in one fancy word, like multiplicants. What? What, Sammy?
The product? What are you trying to find?
No, it's just, can you ask the question again? I know you'll be quiet, Thomas.
What are you trying to figure out?
What?
Oh, never mind.
No, I can't hear you well. I heard the never mind perfectly.
Oh, Ugh.
Yeah, but the question before I didn't hear it well. Um,
What,
so
what's the word? What's the word that you want to know?
I'm looking for a word in Hebrew when you talk about the elements, the members participating in the multiplication in machpelah, they're called muchpalim. So you told me that the word, the English word is multiplicants for the elements participating in the multiplication. I asked him another question: what is the equivalent word for members of sum, of a summation? If there exists such a word. What?
I'll type it.
Without the word sum in it? No, I don't know. Okay, so I write down in the chat. Summons. Maybe. Maybe like multiplicand. Maybe it's the word. I don't know.
Yeah.
Summons. All right. Yeah.
And then
Dance with AD. No, it's not, it's not a word. Simon says not a word. I don't know. Okay, listen. What do we achieve? We get the same result multiplying by v and u for every vector we want. It is the same for every u and every v. So the matrices must be the same matrix. And so by conjugating both sides, we get that the representing matrix of T star is indeed the conjugate of the transpose of the representing matrix of T, which is star by our notation about matrices. Okay, any question about the proof? So let's write down quickly the basic properties. Properties of the star operator. Star linear summation. I don't want this here. Not it that way. First of all, if you star a sum, you can star each one of them. When it comes to the matrices themselves, it's pretty easy to understand because the sum is the couplets conjugate, the star is the couplets conjugate, and their transpose, which are known to be both linear and whatever you want. But here you should go to the matrices through the orthonormal basis, so it's not extremely trivial. But after write down all the properties, we can choose one to prove. Alpha T star is the conjugate of alpha multiplied by T star. Oh no, is it what? Third, if you look at the star of a multiplication, or more precisely, it is a composition of two linear functions, then you put the star and you switch the order, not something very new. And of course, if you look at the star of the star, it's the original linear transformation. Let's prove one of them. Let's prove A. We can use the definition of the using the inner product, T on the left, the star on the right, but something is sorry for that. I need to stop screen sharing and continue. So I started to say we can use definition with the inner product. We can use the representation with matrices using orthonormal bases. Why aren't you writing? Let B and C be orthonormal bases of U and V, okay? And let S and T from U to V be an orthonormal, be a linear transformations. And of course, U and V are inner product spaces over a field F, yeah, whatever. So we know that the matrix of S or T plus S star by B and C is the star of the matrix of T plus C from C to B. Oh, no, if it's T from U to S, no, it's the other way around. By the way I wrote down these letters, it's from C to B, and this is from B to C. And T star again. And you know what star is? It's the transpose and the complex conjugate. Now we know that the representing of a matrix using bases is a linear transformation. It is the matrix of T plus the matrix of S. And when everything is linear, everything is linear. We know that it is the star of BBC, no, plus the star of SBC. It is indeed T star, or at least this is the matrix of T star from C to B plus the matrix of S star from C to B, which is the matrix of T star plus S star. Yet again, the representing with bases is a linear operation. We can take out the sigma, the summation if we want, and it is the same. The two linear transformation has the same representing matrix using the same bases, then they must be the same linear transformation. The linear transformations have the same matrix for the same bases. So they are the same linear, again, linear transformation. Now there are three things here that I know that satisfies the linearity property, and I use it. The first is the representing linear transformation with a matrix with bases. It is linear. This is this equality and this equality again. And I use the star, the linearity of the star, which is linearity of the transpose and the linearity of the complex conjugate. Okay. Any questions about my proof here?
Yeah, I've got a question.
Yeah.
I'm just confused about why you're using the C, B, and B to C notation.
No, you should or write it down in the chat, or I don't know, when you said never mind earlier, I heard you perfectly. I don't know why it's working so well. Why do you use a C to B notation? I mean, I'm trying to use the following. I'm trying to use my last part of the theorem that we can talk about the representing matrix using the basis C and B of star using the matrix of the linear transformation itself, the original one. So when I look at a star, I look at the star of the corresponding matrix. And when it comes to matrices, on one hand, when it comes to the star, on the other hand, I know that linearity is satisfied. I can use put inside, outside the summation or the multiplication by a scalar if I prove V, which is not going to happen. We need to move on. And then I get my proof. The same matrix for the same basis, so it has to be the same linear transformation. Cool. Okay. So we move on to our next subject. We probably continue it on the next lecture. Let's see how much do we achieve today. I call it spatial operators. What is an operator? Just a quick reminder. A linear transformation from a space to itself is called linear operator. Okay. A linear transformation V from V to V is called a linear operator, or just operator. Don't have different operators here. Now let B blah blah blah. Let B be an inner product space over field F, and let T from V to V be an operator. Because T is from V to V, T star is from V to V as well. First of all, T is called normal if T and T star are can be changed. מתחלפות in Hebrew. How do you say about matrices in linear algebra 1? When AB equals BA, do you have a specific name for that?
I mean, I think it's complicated.
They are commutative, whatever. T is called. And let's check. I'll check myself or track myself. How do we actually say it in English and not just my literal? Well, okay. Normal is called normal in English as well, which is not surprising. It commutes, yeah, T commutes with T star. Yes, in English you call it the, oh, it's not written down. What? How do I say it in English? I can ask GPT, but well, I don't know if I trust it. Okay. T is called Hermitian, which is already a word I used, so it's not very good. T is called self-conjugate. I don't know. Well. Self-conjugated.
Yeah.
Yeah. Conjugated or Hermitian. Hermitian. I always use the word Hermitian, so it's problematic. If T and T star are the same. Thirdly, is called anti-Hermitian. If T is the minus of T star. And 4, T is called unitary if the inverse of T is T star, meaning that EI is the meaning or an example, I always forget. T multiplied by T star is I. Over R, the field is the real numbers. It is called orthogonal. Orthogonal operator. When T minus 1 is T star, notice that over R, it's all just transpose without the star, without the complex conjugate. And notice that if T is Hermitian or anti-Hermitian or unitary, it must be normal. T is T star, well, T commutes with itself and commutates or whatever the word is. And for anti-Hermitian and unitary is practically the same. Okay. We want to discuss not just today what's left from our lecture, but also probably on next week. And I want to discuss this kind of operators, and we can say the same. Can define or call the same for matrices, for square matrices. Matrices A that being F of n multiplied by n. A is called normal if A commutates with A star, and so on. Now, what do I say about the connection between the matrices and the linear operators? Proposition, something similar to what we've already said today. Proposition. Let B V space and let B blah 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 be an operator. Let B be n orthonormal basis of V. Then, first of all, let's write it down that way. Then T is normal if and only if the representing matrix of C from B to B is normal, and the same goes for Hermitian, anti-Hermitian, and unitary. The operator is unitary if and only if the representing matrix using B, whatever B is, as long as it's an orthonormal basis, is unitary, and so on. We can prove it. It's practically the same for each one of the statements here, 4 of them. So let's prove the 4th one. We prove that P is unitary if and only if the matrix T from B to B is unitary. Indeed, T is unitary T is unitary means that T star is I, if and only if the representing matrix of T star from B to B is the same as the representing matrix of I from B to B. Now, on one hand, by one of the rules of representing matrices, we know that the matrix of the composition T star is the multiplication of the matrices of T and T star. And on the other hand, the representing matrix or the transformation matrix from a basis to itself is just I. Just have I here. And using our theorem here about how do we check the representing matrix of T star, when we use it for the same basis B, and first of all, instead of P and conjugate, let's just write it down as star. When we use it for the same B, we get here that T star from B to B is the star of T from B to B. So instead of T star from B to B, can write it down as T from B to B star. Here we did get the very definition of unitary matrix about T from B to B. You multiply T from B to B with its star and you get I. So it is indeed if and only if T is unitary, T star is I, if and only if T from TBB is unitary, TBB multiplied by its star is I. Okay. Any questions about that?
So normally that is commutative and then
Okay. Okay. Any questions, the Zoom links? So we know now want to start talking about receipts next week probably more to elaborate more. We can define or phrase or whatever some criteria for the normality and the unitary being unitarity. That's what we say, probably. Let's write down unitarity. Yes, unitarity for of linear operators. We have something like 10 minutes, even less, 9, even 8. But you calculate it. So I will start today with criterion for normality, and then we will can write down a criterion for unitarity. You know what? Let's start it. Theorems. Let V blah 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 blah. Copy and paste. Then P is normal if and only if the norm of TV the norm of TV and the norm of T star V are the same for every V. This is the criteria for normality. We can prove it, or we can write down the criteria for unitarity. There's only one criterion, but for unitarity, it will be criteria. You just rush it out. So now I write it down, and then I just think to myself, am I willing to prove it? Let V blah 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 operator. Then the following conditions are equivalent. Each one of them is if and only if with the other one. With the others, A, T is unitary, meaning that multiplying it with its star gives you I. And of course, T star T is I as well. Secondly, T preserves, that's what I call it, preserves the inner product. What do I mean by that? I mean that the inner product of TU and TV is just the same as the inner product of U and V themselves for every U and V in V. T preserves the norm. Meaning that the norm of TV is the same as the norm of V for every V in V. And T preserves distance. It can preserve angles as well, but T preserves distance. Distances, what do I mean by that? I mean that the norm of the difference between TU and TV is the same as the norm of the difference between U and V for every two vectors U and V in our inner product space V. It means that in reality, yeah, it's a big word, unitary operators / unitary matrices are very important because they preserve the distances and the norms, which is distant from the origin, and they moreover then they preserve the angle. We define an angle then the inner product divided by the multiplication of the norms, and so on. Every, for example, movement in in some game in your computer, yeah, is defined by multiplications of unitary matrices. I mean, I'm the player. I don't want the player to stretch when he goes right or left. I want him to stay the same size. I mean, the distance between the hand and his eyes should be always the same, whatever, no matter how I move it. And so on, all the graphics should stay the same. Even I've changed my point of view. I mean, the distances between 2 points is the same, no matter if the player look at them from here or from there. So the moving of the screen itself is, as I mentioned before, some lecture before, multiplication by matrices. And moreover, these matrices should be unitary in order to preserve the distances and the angles and whatever needs to be preserved. I can write it down. Note by our theorem, or the corollary, that's what we call it, right? Corollary. If T is unitary, then T preserves angles. What do I mean by that? I mean that the angle between TU and TV, which is the multiplication of TU TV divided by the multiplication of its norms, is the same as the multiplication of U and V divided by the multiplication of V and U, or U and V, whatever. But it's not true vice versa. Yes, if on the other hand, if T, it's a small line, if T preserves angles, it is not necessarily, that's how we write it down, unitary. For example, T of U is just 2U. You multiply the vector by 2, what's the same angle, but the distances are multiplied by 2. We have this intuition from the basic Euclidean geometry from high school or even middle school, knowing that the triangles has the same angles, they are not the same triangle, not necessarily the same triangle. They have the same shape, but they're not. Yes, it's called similar. And not how do you say Hafafim? Congruent triangles? Congruent, no? Congruent. This when two triangles are basically the same, how do you call it in English, Sammy? Congruent, when you know that two angles are the same and one edge is the same, so they are actually the same triangle.
Yeah, congruent.
Congruent, yeah. So it's called congruent. So angles are not enough to say, what's the same triangle. So here, angles are not enough to say, what? The operator is actually unitary. I mean, if the angle between 2 points at the screen are the same, but now they are far more distant from each other, probably won't be a good computer game. Okay, we can, not now, but we can, of course, prove we can prove that these criteria is true, and the first criteria for normal operator is true as well. We don't have the time today. I'll think about it with myself. Maybe we'll prove it after, of course, a beautiful fat reminder next week, or maybe we can move on using what we've already learned. Okay, any questions about our material? Linear algebra 2, linear 2, algebra 2, linear Linear tree, the first of algebra. Never.
Linear dimension vector.
Yeah. So you do you as well. As always. 3 o'clock. 30 minutes from now, we'll meet at Infi. May we meet again.